sorted. So welcome to this edition. Today's speaker is Professor Abdul from the University of Witwatersrand. Abdul studied at university at WITS and climbed the academic ranks at WITS from lecturer to full professor. Yeah. So he's really a dedicated WITS person. Yeah. Already during his PhD thesis, he started being interested in symmetries in and around us. Yeah. And I think the plan is that he would explain us something more about symmetries this afternoon. Yeah. So Abdul, thank you very much for being with us today. And we are very much looking forward to your presentation.
Thank you very much, Professor. When you said climbed, and I thought, is this another climbing experience for me? Every time something happens to me, it's got to be doing with climbing. I mean, it's like, you hurt yourself. Did you climb? You know, you fell over something. Did you climb? So when I hear the word climb, something happens to me. Anyway, first of all, thank you, Professor, and thank you to NITheCS for giving me this opportunity of speaking in a cinema. I have a small son whom in Afrikaans we call a laat lammetjie. It means he came rather late. And he keeps telling me, you know, Tom Cruise is about your age, but why does he look so young? It's like, I just feel like, listen here. So I now can tell him, you know what? I'm doing what Tom Cruise does. I'm in a cinema and I'm supposedly on stage. So I hope some way you will at some point see this video of me talking. I mean, obviously he doesn't, when you tell him things like this, he literally says, just keep quiet and let's move on with life. Although he'll ask intelligent questions, but when you pose intelligent things to him, he'd rather play ball or ride bicycle and things like that. So before I get into the topic on symmetries, I was told understandably that the audience here will be not just from mathematics, not just from applied mathematics and engineering, but there'll be some general audience, people in the audience or online who have some ideas of mathematics, will be interested in mathematics, but would not know the mathematics behind it. Which reminds me of a book by Stephen Hawking. You know, when he wrote, some of you must have read this book of his, A Brief History of Time. So in the introduction, he speaks about two things, at least two things. He says, he noted from Bertrand Russell that you must be able to explain your mathematics to a barmaid. Well, that sounds okay, because it means if you can do that, then you have a pretty good ability to explain or bring down the level of your mathematics. So I grew up in a shanty town. So when I heard that, I went to the local shebeen, see? And then there was the lady working there, and I tried to explain about the mathematics part of this, you see? And she just told me, hey, Wena, which means you're just disturbing me. Amba. Is that just go and don't ever come back. So Russell's idea didn't work, at least for me. The next thing he does mention in the book, and that was important, is that when I think the publishers asked, or when they had this agreement to write the book, he was told that if for every equation he's going to put in that book, he's probably going to use half the number of possible readers of the book. And of course, he does. I think he does try to do that. I read parts of the book, and he could not resist the temptation of putting one equation in them, which was the E equals mc squared. And he was very careful about that. But as you go along in this book, you do see equations coming in. So there will be equations eventually. And at that point, if I see anybody leave, I will call you back. You know, we are experienced teachers, so we know how to deal with students like, hey, come back here. So about symmetries, and I'm going to speak about symmetries in nature, and then of course we'll go into the mathematics part of it and so on. So forgive me when it becomes mathematical and technical. Okay, so let's start with nice pictures, and I hope this thing works. And please forget, there we are. So we know the classic ideas or interpretations of mathematics as we see it in the real world, right? You've got the, which is generally symmetric. But when we speak about symmetry, right, in nature, in general, there's always a reference, right? Which is not just symmetric. For example, if you look at the B along the reverse diagonal, it's not symmetric, right? So you have to have a reference. So the B in that picture, in fact, the butterfly and the leaf are symmetric about some line that we accept, right? And of course, the leaf sometimes and I look at properly, it's not exactly symmetrical in terms of the veins and so on, but we regard that as a pretty symmetric structure about the main vein, about the center line. So that kind of symmetry we fully understand, and that essentially is usually our starting point for what we regard as symmetry, right? And so this one is in all of these cases, it's really reflexive about some line, and it's beautiful. It makes life beautiful, it makes the world beautiful, and so on. But when we speak about symmetry, I'll go beyond all that. Okay, and the one thing I want you to keep in mind is that, in a sense, discrete symmetries. In a sense, it's just on the fold relative to this line. Right. So getting more onto the mathematical side of it, still sticking to pictures. If you look at an equilateral triangle, well, if you have to rotate it about 120 degrees, it looks the same. So now I'm bringing the notion of symmetry into the concept of things unchanged in terms of appearance, right? So if you go from left to right, a rotation of 120 degrees, the triangle remains the same. So if you rotate it, you know the difference. It's symmetric. Rotation symmetric about a specific angle, 120 degrees, not randomly. If I rotate it about 90 degrees, it will not look the same, right? In terms of its position there. There's other forms of symmetry built within that. So, and it's clear from these pictures what I mean. So you've got those dotted lines around which this thing is internally symmetric. So there's two notions of symmetric already in that picture. The one is symmetry means that when you do things to it, it still looks like it was. That's in the first line. In the second line, second row of pictures, you've got the symmetry about, like in the pictures of the butterfly and so on. So there's various notions of symmetry. Here's another nice picture, right? So the circle has all kinds of symmetries. If you reflect it about the diameter or any diameter, it's some sort of reflexive kind of symmetry. Similarly with the second two pictures. I want to go back. And the back doesn't work, so let me do this. Forgive me when I do these things. At this point, I just want you to stop for a while. Hang on. The difference between, or the special thing about a circle as opposed to, say, the equilateral triangle. So in the case of the equilateral triangle, you're rotating it about, now watch this, it's like this, 120 degrees, 120 degrees. It's a jump, right? Whereas in the case of the circle, any angle rotation, it looks the same, right? So on the one hand, you get what I'm going to eventually refer to as a discrete symmetry. It's boom, boom, and it looks the same, 120 degrees. Whereas in the case of the circle, and the word I'm going to use here, it's going to come up quite often, it's a continuous symmetry, continuous rotation, which leaves the circle the same. And I want you to just keep those words in mind when I get to the formal definitions later. We've got the discrete symmetry, and we've got the continuous symmetry. And the circle is the one so far that satisfies the notion of a continuous symmetry. So any angle, if you rotate it by, it looks the same, right? So it's unchanged visually. This is going to be interesting. Let's hope it works. I love movies. That's my problem. You know, things in the context of a movie. I mean, I started off with Tom Cruise, for example. Now let's hope this works. And I want you to listen out for one important word there. And I hope we get sound here. This is a scene from Elementary. Listen.
Symmetry, I'm trained to be on the
I'll play it louder.
You're beautiful. Symmetry, I'm trained to be on the lookout for it.
I like that. Oh, so Moriarty is telling Sherlock Holmes that symmetry, that's what I'm looking out for. She plays a painter and so on initially. The thing I'd just like to let you know this, by the way. So in one of the series I was watching on QI, they questioning various things. And the chairperson there asks the panel, would you want to have symmetric knees or would you like to have a symmetric face? So generally people go for the face, right? Turns out that they had this little thing to play with. So each of the panelists, without their knowledge, the pictures was taken and a symmetry was done of their face. So the one half was taken and that was superimposed in the reverse direction on the other side. The trouble is, they did not look so nice anymore. Some of those characters look like characters out of Star Trek. You know, weird, really weird. So one has to be careful about symmetry being pushed a bit too far. So we sometimes think that we are symmetrical, but it doesn't quite work that way. So the notion of symmetry taken in the other direction is the notion of symmetry breaking or asymmetry. And it turns out that sometimes in nature, and those of you involved in cosmology and so on, you come up with this concept of symmetry breaking. So the symmetry breaking sometimes might produce a better picture, better understanding of the reality. So I'll just play that by the way. Okay. Now I mentioned there about these kinds of symmetries that occur in nature, the discrete ones. The nice thing about the circle is the continuous ones and so on. The trouble is when we talk about those nice discrete ones, that's not what I'm going to refer to in my talk. I know you're going to be disappointed. I mean, you talk about all these nice pictures, you put in these butterflies and so on, but that's not the symmetry we're going to talk about. When you come to differential equations and equations in general, it's another notion of symmetry that I want to speak about. And will work very well in terms of describing, dealing, analyzing equations, and beyond that, differential equations. So, yeah, now I'm going to get a bit mathematical, but just bear with me. So, what happens in the case of a circle? Let's go back to the circle. I think whenever you have whenever I lose you or you lose me, go back to the circle, right? What did I say about the circle? That the circle looks the same. I'm defining that as symmetry. It is invariant. It doesn't change no matter what angle you rotate it through. Now let's get a bit more technical. So what's happening is that if I choose an angle from a set, and think of an angle as any number, right? And I say, well, choose some angle, pi by 2, 45 degrees, rotate, looks the same. 45.1 degrees. Any angle you choose from this little set and which instructs the circle rotate, it will rotate and it will look the same. In other words, what we have is I can take my set of values from a continuous line, one parameter, continuous line, and impose that onto the circle and it will continuously remain the same. So now we get the notion of what? We've got a notion of a set that has these continuous variables, like a real line, that is instructing this circle to behave in a particular way. In our case, rotate continuously. So we have the notion of a continuous set, a set of continuous values, and acting on the circle, which I'm eventually going to call a manifold when I generalize. But no matter what I do, it remains the same on the side. Keep that concept in mind. So it's, in general, what it means is the following. Choose an angle, choose a number from the real line. We know they are infinite, they're continuous. Just choose any number from the little set that just says my angles were chosen to instruct the circle, and then act on some point on some manifold. By the way, the manifold is essentially just anything that you can put in Euclidean space. I can take my sphere, which is in R3, it's already Euclidean, but I can open it up, and we know how to do that. You see this in second year, third year. You can open your sphere up, you can take your cylinder, you can open it up, and embed it on the plane. So it's a two-dimensional manifold. Any such manifold I have on this side, so I choose a value on this side, put it on a point, and transform that point to another point from x to x bar. And these are all in coordinate form. Then I say choose another value like beta. Act it on x bar to get x double bar. And keep in mind that because this is a real line, the alphas betas can be chosen anywhere along that. And I want this kind of change. So if I were to choose values, say between 0 and alpha, it's going, you're starting off with x and it's moving until it hits x bar to alpha because of alpha. Then choose values beyond alpha continuously. The word is continuously from alpha to beta, and moves that x bar continuously bang onto x double bar. So we've got this continuous transformation. We've got the continuous and we've got transformation. Continuous transformation. It's like the circle is continuously being rotated, and it still looks the same. So we want it to be doing it in the following way. We want the following two conditions to be satisfied. That if I go from x to x bar, because of alpha, and from x bar to x double bar due to beta, then I would like the following to happen. But if I were to choose these values from my little set on the left-hand side, my one parameter group, if I want, and do an operation. Now in the real line, what kind of operation can do? You can multiply, but I'm going to choose addition. That specific operation. So I take these two values, add them first. Take alpha plus beta. Then act on x. And what I would like is that from x, if I were to take alpha plus beta acting on x, then it goes straight from x to where? X double bar. That may not always happen. But if my formula that transforms x to x bar to x double bar is such that when I do the sum, alpha plus beta on x, I'm going to go straight from x and I land at the same point, x double bar. Option number one. So my transformation formula, the thing that is transforming my points on this manifold, I'd like it to satisfy that property. Alpha plus beta should give me the same thing as alpha first, then beta. And if I were to take the identity, which in the case of the real set with the addition as the operation, if I take 0, the identity, and act it on anything, that anything should not be transformed. It stays where it is. Just these two conditions. And when these two conditions are satisfied, we say that that transformation, that act, that map, is called a, listen to this, one parameter, I'm taking one parameter set. It's a one parameter transformation of whatever manifold is working on. And we give it a name, we say it's a one parameter Lie group transformation. These two conditions have to be satisfied in whatever formula I'm going to use to transform the points on my manifold. So this whole thing about symmetry is resting around the following. That the points on my manifold where I'm acting things are going to be transformed. They're going to be transformed continuously. They're going to be transformed by the action of a single parameter. And then I want these two conditions to be satisfied. And when that happens, I'll call it a one parameter Lie group, Lie after surface Lie of transformations. And when that happens, the world opens up. Let's see. So this is just a summary of what I was saying previously, that you want to go from x to x bar to x double bar, and you must be able to go from x to x double bar if you started off with the parameters collected on the other side. Right. Yes, I hope I don't lose half of you. Turns out, well, condition number one there It's exactly what I said. You're going from X bar to X double bar. And you want it to be the same as if you added the two and you ended up at X double bar. That's just what condition 1 is. Condition 2 is saying that like the identity is 0. If you add the identity in any point, it remains the same. That's number 2 there. If these two conditions are satisfied, we have a Lie group transformation. But it's continuous, keep that in mind. It's not discrete, like the equilateral triangle. Now it turns out that if this transformation satisfies that, you can represent the transformation. I'm not going to get into the details, of course. You can represent that same transformation, this transformation of this action x to x bar to x double bar, vector field form. Some of you will recognize this as a partial derivative operator. You can represent it in this form. And if I give you a transformation in this form, you'll be able to, again, by some formula and so on, get back to that Lie number 1, 2 condition. So in the case of a Lie group transformation, you can represent them as vector fields. There's the vector field. And if I give you a vector field, you can regain the actual transformation. That's a theory part of it. So what's happening here is we'll be given things like x bar, and you are dealing with, say, 2, 3 coordinates, x bar, y bar, z bar. These transformations satisfy conditions 1 and 2. You can rewrite those as d by dx, d by dy, or d by dz in terms of a partial differential operator. It's a vector field representation. So this is what can be done. This is essentially what I said, that you can rewrite a transformation as a vector field. Don't worry about the first part. Now, this is where Lie comes in. What Lie showed is that, well, what is the advantage of this? That if you can use these transformations, then the next question you can ask actually goes to before Lie, to Gallo already. You can identify functions that are functions that are left unchanged, form unchanged, if you make these substitutions. Let me give you an example. If you look at the equation of a circle now, I try to remember the equation of a circle, x squared plus y squared equals some constant, right? Now I change the x's and y's to x bar, y bar. And I ask a question like, what x bar in terms of xy and what y bar in terms of xy will leave that equation as x bar squared plus y bar squared equals to the same constant. Okay, and you'll see the result of that. So this whole business of one parameter Lie groups of transformations hangs around. It depends on finding functions that are left invariant, that are left unchanged, and there's where the symmetry part comes in. That you want things to be unchanged, even though you transformed the variable. You go from xy to x bar, y bar, like in the case discussed there in general. But not only is it just going from xy to x bar, y bar, the change from xy to x bar, y bar satisfies those two important conditions that renders it a one parameter Lie group of transformation. We are now going to look for functions that are left invariant, form unchanged. It all hangs around that. And every one of those, we said, can be written in a vector field form. Here's some example. If you're dealing with, in the first case, variables say x, y, and t, then if you look at that first line, x bar, x, that x's are not changed. The y's are not changed. But the t has been transformed from t to t plus a constant. So if you've got like 3 coordinates, suppose t is one of the coordinates, your x's remain the same, your y remains the same, but the t's have been just translated. It turns out that the vector field representation of that one parameter Lie group of transformation is this d by dt. Just think of d by dt as representing transformation in t. Now here's the nice one. If you deal with 2 coordinates x and y, all of you would have seen this in first year algebra somewhere, that if you were to transform from x, y to x bar, y bar via this formula of x bar and this formula of y bar, depending on x and y, you get rotation through that particular angle. Rotation of x is where you've seen it. This is the one that represents rotation. And the corresponding, if I were to use that x bar and that y bar and convert it to a vector field version, this is what I'll get. Vector field form. So this, think of this as a representation of, an alternate representation of the one parameter Lie group of transformations. So built in here in the vector field, capital X, is a formula that converts xy to x bar, y bar. Using what? One parameter at a time. In this case, the parameter will be beta. And what that does is it will rotate your circle to an angle beta. But it could be anything. It's continuous, any angle. And notice what it's doing. It's doing this continuously. Continuous transformation, leaving the thing the same. In the first case, you're having translation, the x, y's are remaining the same. But your transformation is only the t. But the t is just being translated. It's continuous. Continuous translation, continuous rotation. That's what we're discussing here. The next step then is to ask the question, what functions of x, y, and t, what functions of x, y, and t are left unchanged when we make this changing variable? Because when you're going from x, y to x bar, y bar, you're changing variable. But you're asking the question, what functions are still left the same even though you're changing things? Now, those kind of questions was asked way back in the time of Galois and was used to determine the invariance or studying invariance of algebraic equations. And that's where you got the discriminant and so on coming, which we study at school. Here's a nice example. You see, so you got x bar, y bar satisfying that change from xy to x bar, y bar. It turns out if you test the two conditions, they're satisfied, it's a one parameter Lie group of transformation. We can show, and because it's a one parameter Lie group of transformation, we can represent it in terms of a vector field, and the vector field version is exactly there. So the x's have been expanded, the y's have been reduced. Either way, we call it scaling. Scaling up or scaling down. Dilation or scaling down. So there's another one parameter Lie group of transformation in vector field form. X represents space, T represents time. This one comes up in the equations of cosmology and so on. That one looks like rotation. So space variables, on the previous slide, you got x d by dy minus y d by dx. That was rotation in x and y. But this is plus and t is time. So this one has been interpreted as Lorentz rotation in the literature. Right, now we're getting a bit technical. What we want to do now is say, how can I, given a differential equation, how can I identify the changes of variable in my differential equation now that will make the differential equation form invariant, that it looks the same? So if I give you something like, in terms of small x and y double dash equal to 0. Now I want the xy to be changed to say capital X, capital Y instead of x bar, y bar. Let's call it capital X, capital Y. So I want the transformed equation to be also y double dash equal to 0. The equation has been unchanged. The question is, how do we do those transformations? How do we find those transformations? And it turns out, and this is where surface Lie comes in. So now this is just technical definitions. We need these concepts for to do the theory and so on. I don't want to get too much into that. What Lie, essentially, I want to get to Lie's theorem. And this is Lie's theorem. It goes like this. E is the differential equation. That could be y double dash equal to 0 in for ODEs. That E could be your heat equation, your KdV equation, if it's more than one independent variable. So you've got your equation. X represents the vector field as before. And what Lie showed is that if you wanted to identify, you wanted to find the vector field equivalently, the one parameter Lie groups of transformations that leaves the differential equation invariant, that is what you solve. So your E is known. That's your left-hand side of your differential equation. What is unknown are the x's. And what the solution of that equation will give you are those, if you're successfully solving that, will give you a vector field will give you the one parameter Lie groups of transformations that take your differential equation and leave it invariant. He showed this is what has to be done as long as you stick to the differential equation. Now, this was really the nice thing about Lie's theorem. Remember what I said earlier? Your one parameter Lie groups of transformations have the form x bar y bar. It can be written as vector field. The nice thing is, if you got them in vector field form, to identify the transformations, the vector field form is the one that is nice to work with. Nice meaning your calculations become all nice and simple. I mean, if I asked you, here's a differential equation, find the x bar, y bars that leaves it invariant. You got a serious problem. Because you got to change the variable, you got to change the derivatives, the higher derivatives, and you got partial difference. Oh, man, it just gets ugly. Take your one parameter Lie group of transformation, cast it in vector field form, and all you do is solve that set of equations. Simple PDE, system of PDE. And you may get, and often you do, that you've given a differential equation, it might be left invariant under more than one transformation. And often that happens. You're going to ask the question, why are you doing this? But I'll get to that. So that's surface Lie. You worked on differential equations. Essentially, we wanted to extend the work done on algebraic equations to differential equations. And we successfully did that. Lie algebras, Lie groups, same surface Lie. Then something happened. I don't know if it was the Second World War, First World War. Maybe it was the atom bomb. Something happened. This popularity of this method to deal with differential equations just disappeared, went quiet. Until in the 50s, in the Russian school, in Novosibirsk under Lev Ovsyannikov, this idea, these methods of Lie were rekindled. And this time, like the new Chinese invasion, it was not going to stop. It just caught on, and it just took on and went on forever. Or when I say forever, I mean until now. So from here on, from the 50s, these methods have been developed to deal with the theory, to deal with the algebraic properties, the applications. Then applications even went further, not to just single equations that we know, the popular equations like heat equation, KdV, Berger's equation, but went on to deal with systems of equations, equations that come up in fluid mechanics, in relativity. And it just went on, which is nice. And it hasn't stopped yet. And I'll mention at the end that it's gone even beyond differential equations. Lev Ovsyannikov. The interaction with him was when he came to Johannesburg. He wanted to see the city, so I took him to see the city. And in the lift with other Russians, they're trying to, we wanted to buy something. And there was this major debate or discussion about what is it that you're talking about. It turned out that I understood Russian why, but later I realized that to him it was important. He was looking for a coconut. He mentioned the word in Russian, I don't know Russian, but it went on, and then eventually we sort of worked it out and we got a coconut. And we were extremely happy. So something that we take for granted is like this coconut. And by the way, so beyond that, students of Lev Ovsyannikov, for example, Niall Ibragimov, I mean, really took the work very far. And he even, I got a little story, came to South Africa, and when he did, it's going to be a play on words. He came home, and this is Ibragimov, Russian. And we eat leeches, so we served the leeches, and never saw the fruit. Like, he was really enjoying it. Amazing. What's this fruit? Leeches. At my place. Please don't sell this to Peter Leach. Peter Leach brought this method. Leach. Just hang on. You might have eaten leeches in my house, but the Leach is responsible for bringing the methods of surface Lie to South Africa. So every one of us are, in a sense, indebted to Peter Leach, who's brought these methods to South Africa. Okay, let's stop there for a moment. That's differential equations, right? That is symmetries, invariants, one parameter Lie groups of transformations for differential equations. What do we do with them? Well, we first of all, given the differential equation, we have a algorithmic way of finding these. And these days, there are software packages that can do that for us. but we have to be careful, of course. And the work has gone on and has taken on amazing directions. Now I want to speak a little about another aspect of differential equations which come up in applications also, the notion of conservation. Now, to the physicists and to the mathematical physicists and the engineers, we know about conservation laws, right? These are ones that deal with conservation of momentum, conservation of energy, and those kinds of things. And what I want to look at here is the mathematical interpretation or the mathematical aspect of conservation laws. So I put the equation down there. Essentially what it means is, mathematically, if you can take your equation or a system of equations and write it in conserved form as a total divergence, that is a conserved form, you have a conservation law. And associated with the conservation law is a conserved vector. So your T's, you can find them and rewrite your equation in conserved form. The T's will be called conserved flow or a conserved vector. So there might be a component there that comes from the time variable. That component will be called the conserved density. There might be a component that's got to do with the x variable space. We can call that a conserved flux in the x direction. There is some kind of physical interpretation of these. So for us, the differential equation, E equal whatever, write it in conserved form, you have conservation law. Done. Right. What do we do with symmetries of differential equations? And what can we do mathematically with conservation laws? Well, I didn't get too much into this, but if I gave you a differential equation and I tell you, here are the symmetries, the vector fields that leave it invariant, what can you do with that? Well, there's several things. You can show that you can reduce the order of the differential equation. That's essentially what you're doing when you're solving differential equations. Order means what? ODEs from third to second to first order. Or PDEs could mean that, and it could mean reducing the number of independent variables. Your vector field that leaves the differential equation invariant can be used for this, for a start. You can even use them to cast things from something complex to something simple. It turns out, for example, that each of these differential equations, once you find the vector fields that leave it invariant, they form an algebra. I don't want to get into the details of algebra. They form specific structures, the algebra. And in two differential equations, completely different differential equations, generate the same algebra. You can map the one to the other using the vector fields that you found. Why would you want to do that? Simple. You have a complex differential equation with a certain algebra it generates. You have a manageable differential equation which generates the same algebra. You would want to map the complex one to the manageable one. And what do you do next? You solve the manageable one and then you transform back. So that's another reason why one deals with these vector fields that leave the differential equation invariant. With conservation laws, you can do something similar. You can essentially reduce, because we can show that you can write the differential equation as a manageable system, and you can reduce the differential equation. What's the next question you're going to ask? We have a way of reducing equations using these transformations that leave it invariant. You have conservation laws that can be used mathematically to reduce. What if you have both? You can do things twice. You can reduce with this, and you can reduce with that. For example, if I gave you a second order ODE, you can use maybe the transformation to reduce it once, a corresponding conserved vector to reduce it again. You got a solution. Okay? So as long as you can use the vector fields that leave it invariant with the conservation law, which should have some relationship. Keep that in mind. So this is just an alternate definition of finding conserved forms for differential equation. Differential geometers prefer to deal with 1 and 2 forms and so on. I won't get into the detail of that. Right. So enter the work of Noether. Now stop. Let's speak a little about Noether. So about this time, we had this particular problem. So it was about relativity. I mean, Einstein's work was really taking on and became the popular thing, you know, like the movies of Tom Cruise. So that world was speaking about relativity. What keeps things conserved? What keeps what kind of mathematical structures to the differential equations have and so on. And the one question that has been bothering a lot of people at that time is, what was the relationship, a technical relationship between what I spoke about first, vector fields that leave your system invariant, exactly what I was speaking about, and conservation laws. And when you got that, what is physical about your conservation laws? Because conservation must be physical. There's something to do with energy, and what about the vector fields that leave the energies in store, in place? Your angular momentum, your linear momentum. That's a relationship. And there was always, or rather, there was for a long time, this idea that indeed there was some connection between systems that were invariant in time. They did not change in time. In a language of differential equation, the differential equation was form invariant under time translation. They didn't change in time. And the physical notion of energy. There was this idea, but there was no formal result for that. Keep that in mind. I love this picture that's going to come up. Where is this picture? Here we are. So it was about that time when Felix Klein approached in Göttingen, approached the algebraist, Noether, whose most of her work was in algebra, and she did some real great work, and asked her to possibly deal with a problem in differential geometry, i.e., to identify a possible relationship between systems that are left invariant under time, under space, under these rotation kind of symmetries, and physical conservation. And lo and behold, she cracked it. And she went a bit more. She said, well, she concluded that there is a connection between systems that are left invariant under time, and it implies conservation of energy. Went further to conclude that systems that were invariant in, say, rotation of the variables x and y, for example, implied angular momentum conservation. Systems that were in space translation, that were unchanged in space, implied conservation of linear momentum in that direction. But there's another thing she's done, and that is that she showed, in fact, that you can do this, you can find these conservation laws by a formula. In other words, if I just said, here's a differential equation, find the conservation laws, you'd have to go through the definition and all the mathematics and so on. That's where you get mathematically. What she showed was, in fact, you could take your vector field, plug it into some formula, and boom, you get the conservation laws coming in. And when you get things by formula, we celebrate. And they were celebrated. So in 1918, she published a result of hers, which came to be known as Noether's theorem. So the Noether's theorem is not in algebras, it's in differential geometry. And it's about linking the notion of symmetry with conservation law by formula. I'll speak a little more about that. Okay, here's a picture of Noether. I like this picture. It was an article that Einstein submitted to the New York Times on the occasion of her passing. This is the article he wrote. And this is a little thing I like to mention. So you attended my talks before on this kind of thing. You might have heard this, that there was a mass exodus of the European mathematicians, physicists, and so on to America. Which is expected. I mean, Veblen had just established his Institute for Advanced Study at Princeton, and he was even got Einstein to eventually, and Einstein agreed, and he was a professor there, and there were many others. Noether was one of them that left Europe for America. She gave a lot of lectures all over, and she never had a position, not at IAS or any university in America. Why? Because she was a woman. Simple as that. It's like, America at that time. So, I mean, she did a lot of work. She gave a lot of lectures and so on, and it may be that Einstein recognizes, and that's why he felt a bit bad about it and wrote this article. That's just, by the way. So it was not just, according to what I said, it's Felix Klein, it's also David Hilbert that approached her to develop this possible result between symmetries and conservation laws. There was one little thing that Noether's results depended on. It's not a little thing, actually a big thing. It says that if your differential equation was derivable from a variational principle, and this was the condition it depended on. That means that if there was a Lagrangian for the first system depends about potential, kinetic energy, etc. So if your system had a Lagrangian derivable from your system was derivable from a variational principle, optimization, etc., then if you have these vector fields, specific kind of vector fields, you can construct these conservation laws through formula. This depended on the existence of these Lagrangians. The unfortunate thing, which of course, I mean, it doesn't discredit any of that work, which is amazing work, and was used a lot in physics and mathematical physics and so on. But it's just that a lot of the equations in mathematical physics were independent of or were not derivable at all from Lagrangians. They were not variational at all. And there's a whole class of equations, your heat equation, your Burger's equation, your KdV. These equations do not have a Lagrangian. We have conservation laws. They are vector fields, symmetries that leave it invariant, but you cannot use that but in the manner of Noether to construct the conservation laws. There's no formula for that. If you constructed your classically, you constructed conservation laws for these systems, evolution type equations, you need to use the classic method of the definition, etc. So the question arises, are there situations, or what situation, or what kind of condition needs to be satisfied for one to use vector fields and leave the differential equation invariant to construct conservation laws, similar to what Noether did. Only this time we're saying, suppose we didn't have a Lagrangian. So it must have been a question that went on for a long time. I'll come back to that. I'll just speak a little about where else conservation laws and this notion of vector fields come up. So in differential geometry, when you look at the invariance of manifolds and so on, there's a notion of isometries. There's a formal definition of isometries, famous in Kobayashi's book on studying the transformations in differential geometry. There's the notion of course, what Noether spoke about, of those vector fields. There's the ones that I spoke about. So some are called real symmetries, some are called Noether symmetries or variational, and in the language of differential geometry, they are called isometries. Now, in space-time, when you have these manifolds that are essentially space-time, including time as one of the variables, right? Those isometries are often referred to as tuning vectors. And what we found recently, well, some years ago, is that there's actually a structured relationship between these. So you've got these vector fields, of these spacetimes, which they call killing vectors. They seem to form a subalgebra of the vector fields that are used in Noether's theorem, and those are subalgebras of the classic ones that we spoke about. So you've got this nice relationship, structured relationship, where the one contains the other, contains the other. Really interesting. Some algebraic relationship. So it comes up there too. Yes. Language. Is that all you want? Sorry. Okay. I'm just going to go through one or two methods that have been used in recent times to construct conservation law. So this is going to get a bit technical. So what Stephen Anko and George Blumen, both of Canada, developed is this method of multipliers. So they said, well, if you take a differential equation, instead of finding the conservation laws directly, because sometimes you can't find these, it may be that when you multiply the differential equation by some factor, then the differential equation may have a conservation law. Now, we've seen this before. I often tell my honor students, you've seen it before. And like I said, students never seen anything before. It is a standard result. Time immemorial right to now. Have you seen it before? The answer is no. And when you tell them, do you remember exact differential equations in first year? Integrating factors. What's an integrating factor? And I'll give this look. Well, it's a factor which when multiplied to the differential equation allows the equation to be exact. It's exactly there. So you can take a differential equation, multiply by the factor. You can write it in conserved form, exact form, just like in first year, right? But here it gets a bit smarter. It's like take a differential equation, identify, instead of identifying the conservation laws, identify those multipliers. And what result you're going to use, how you're going to do that? You take the Euler-Lagrange operator on the product, you set it equal to 0, and then you solve for Q's. Now you may wonder, why did that come up? It came from this thing. Now, note that if you go upwards, the curl of the grade is always 0. The curl of the curl is always 0. That we know. And the question is, what of the div is 0? And this is referred to as the variational bicomplex. Right? It turns out it's the Euler operator on the div that's 0. And if you want to go further, not that I've seen any use of this, what on the Euler is 0, it's a Helmholtz operator on the Euler that's 0. But we're interested in that part of the Euler and the div. The div is essentially your divergence. Divergence means you have a conservation law. So that is where that idea came from, that if you operate an Euler operator on a summation of the divergence, it will be equal to 0. So just look for the multipliers they give you there. They just by the way. So this is what their method depended on this little picture. Right. This little slide was an attempt to answer a question I raised earlier. And this was the question. We said that Noether used the invariance of the differential equation via Lagrangian to construct conservation laws via her very nice formula. And the question was, what if there's no Lagrangian? There's probably more equations without that are not variational than those that are, right? And we worked on this, myself and Faisal Mohammed, some years ago, and we developed this result that says that if 510 is satisfied, then what we have, irrespective of a Lagrangian, independent of whether the equation has a Lagrangian or not, it was useful for when equations didn't have a Lagrangian. Because if it has a Lagrangian, go to Noether. But if it didn't, the first thing you would want to do is to identify a relationship between the vector field, the symmetries, or those things that keep the differential equation invariant, as I spoke about first, and its corresponding conservation law. So this result then identifies a relationship between vector field and conserved vectors, and when satisfied, you have a relationship between the two. So why do you want a relationship between a specific vector field and a specific conservation law? Remember I spoke about reduction, that if you reduce a differential equation by a vector field, you get one kind of reduction. You reduce a differential equation by conservation laws, you get another kind of conservation. And if you use a 2, you get double reduction. This connection performs that in the absence or possible absence of a Lagrangian. And it is, the double reduction system was eventually then applied by Ostri Schoberg, who at that time was in University of Johannesburg and so on. And we applied this thing really well into showing how double reduction works for partial differential equations. It worked very well for ODEs until then. For partial differential equations, from here on, it worked. I should just say that the nice thing about the proof of that theorem was we did it using differential forms. How much time do I have? Okay, I'll take 1 minute to discuss how we got into the notion of differential. I like the story. So we had this little result that was trying to do something for 2 independent variables. That's n variables, 2 independent variables. And it seemed to have worked. Ian Anderson is sitting in Utah. And I've heard of him in differential equations. And I think he saw something interesting. So he communicates, he sends a letter. Do you guys remember what a letter is? He sends a letter to say, I think you're wanting to do this. He stated it in the language of differential forms. We know nothing about differential forms. We have to learn differential forms. So we just study differential forms and so on. And lo and behold, we got a general result for any number of independent variables. 1 letter. See? Sounds like a love letter. There's another movie. There's another thing for a movie. Okay, so I was going to do this example, but I will just speak about this example because the details will just not only bore you, it will bore me too. So what did the previous theorem say? It says that if you're given a vector field that leaves a differential equation invariant, you may want to construct specific conservation laws that are associated with that vector field, the guaranteed vector field that keeps it invariant. Why do you want to do that? When you got the two related, you can do all kinds of double reduction and so on. And you can speak about physical conservation law. So what this example does is it says, well, we know that the vector field T dx minus d by d, which is a one parameter Lie group of transformation, calculated in textbook, that leaves a KdV equation invariant. Now we go on and construct a conserved vector. So you're satisfying a conservation law on the equation for it. But you're doing something further. You impose a symmetry condition, the theorem of the previous page. So now you will just not find all conservation laws. You find those specific ones that are associated with this vector field. And if you get something out, now the two will become partners. Double reduction and physical things and all kinds of interpretations and so on. I don't want to get into details of this, but the rest of the slides following this example is about how this is done. What I will say is the following. The notion of vector fields or these one parameter Lie groups of transformations that leave things invariant have gone on to discrete equations, difference equations. These days, it's even gone on to the notion of fractional differential equations. And there are lots of other algebraic properties that have been developed and so on. One of the interesting ones I like to mention that Ali and his supervisor had worked on was to take a set. Suppose you've identified all the vector fields that leave a differential equation invariant, and the question arises, which ones would you like to use to find solutions? So what you're going to do is to classify the subalgebras of that algebra and then construct your best system, which they call an optimal system. I don't want to get into the formal definitions, but you're looking for these optimal subalgebras that gives you this kind of solution or that kind of solution. For PDEs, it works really nice. So that's another thing that is initially started by Lev Ovzhyanikov school and continued, and they've done some nice work in that group of studies and so on. And the notion of those multipliers to construct conservation laws that has been developed by Stephen Anko and Charles Blumen. The relationship between vector fields and those multipliers has also been done recently. And how to use those to double reduce. That has been, in fact, that paper was delivered at our last Symmetry conference here in Stellenbosch. I think I'll stop there because all of this is going to kill half the audience. And you'll get clicks that are going off from the Zoom. Thank you very much.
Very much for the great talks, and
Thank
still we have some time for questions. Any questions? Sorry. You.
So in the first slide, you mentioned the symmetries, and then I saw the picture of a leaf where you saw the leaf. The branches on the leaf are not exactly symmetric, but then I got the idea of the approximate symmetry. I think we need to mention that as well.
Oh, okay. Can I answer? Okay, so another aspect that was developed by the students, well, Ibragimov was a student of Lev Ovzhyanikov, but of Ibragimov students, Kazizov and what was the other guy? Vitaly Paikov. You get sometimes you get your system and you subject it to small approximations. So you take maybe a simple harmonic oscillator equation, right? But you want to introduce a damping term, but you want it to be small. So you introduce a first order epsilon term to kill the continuous movement of the pendulum. So such equations were they refer to as equations with a small parameter, approximate equation. What they did was they developed the whole notion of finding these vector fields that leave invariant equations with a small parameter. And there's a formal procedure. It's not just a random, easy, straightforward procedure. They go through a nice thing, which has its merits and applications and so on. So there's a whole theory behind symmetries of approximate equations. And then when you said leaf, maybe the leaf is God made a mistake. You see, if you look at the picture of the leaf, I mean, what you're saying is the veins on the left do not coincide with the veins on the right. They're like something off. So I think God made a mistake. Like, I'm sorry. But on the other hand, I mentioned the word symmetry breaking. It's sometimes there's more beauty in the breaking of the very symmetry that you found beautiful. And that's why I said, don't try this with some kind of software because you'll really hate yourself. Is this little thing I saw on QI where they took the panel's faces and they switched from to the right and superimposed that on the left. And boy, they look weird.
There's a question here in front, please.
Thank you very much for the very nice talk. I wanted to know, can you explain a little bit how to turn your Lie group, transformation Lie group into a vector field and vice versa? What is the idea?
In the case of Noether, or just generally?
Generally, if there is a general method or if you have to do it case by case?
No, there's a general method. So if you have a one parameter Lie group of transformations, in other words, you've got your formulas that say X bar, Y bar, maybe T bar, transforms like this, right? There's straightforward, I think that is called Lie's first theorem, where you can rewrite that just by doing some differentiations and plugging in initial values, and you get the vector field version of that. And in the opposite direction, I give you a vector field, just a general vector field, which looks like scaling, but you want to see the exact transformation form in terms of the bar notation. You perform set of simple ODEs, get you back to the beginning. Yeah, so there's a formal procedure. And in each case, whether the vector field is in the realm of Noether, isometries, scaling vectors, you can do that. So that part is standard. It is irrespective of differential equations or Noether's theorem or whatever. That procedure is standard.
So next to you.
So you said that if you have two differential equations and they have the same Lie algebras, then there is a way to transform one equation to the other.
Yeah.
Now, what if instead of having same Lie algebras, they produce Lie algebras which are connected to each other by Lie algebra homomorphism? Is there any relationship between these differential equations?
If I've understood this question correctly. So this work has been done for for example, second order ODEs. It's been attempted on third order and successful to some point. And I think, did you guys work on nth order? No, someone on fourth order, nth order. So what happens is you've got these algebras, these Lie algebras that have all been classified. There's two sets of known classifications. The one is the Mubarak-Zianoff one, and the other one is the Patera-Winterner. That was the present Canadian group, right? So they have all the possible Lie algebras that could be of a certain dimension. The next step was, if the differential equations generates these, right, is then what do you do to find this certain way of finding the representative equation in a particular class? So you might have an algebra like SL3R, which is 8-dimensional, right? For ODEs, what will be the representative equation? And then you transform any equation with 8-dimensional Lie algebra to that target equation, which in this case, by the way, is y double dash equal to 0. I'm not sure that.
But what if the Lie algebras are different, but there is some way of connecting the Lie algebras themselves? Does this connection reflect in some sort of connection between the differential equations?
I don't know. What I do know is that, or what is known, what is known is that you could classify the subalgebra, so that works in the case of subalgebra. So you might get a second order ODE with a 3-dimensional algebra. But all you need is a 2-dimensional subalgebra, because you need two symmetries, two vector fields, from second to first order to zero order solution, that kind of thing. Just about an example on mapping one equation to another. The simple harmonic oscillator equation, y double s plus y equal to 0. That generates an 8-dimensional Lie algebra for ODEs. Y double s equal to 0 does the same thing. So you can actually transform the one to the other using your vector fields. That's two simple equations, but you can imagine you can extend this to a rather complex equation. We've done that sometime in the past. Thanks.
Okay. And then, yeah, please. Okay, let's do this. And then maybe we see if we have questions from the online audience.
I had a question. Are there any possibility of spontaneous breaking of Lie point symmetry?
In this work, that's not discussed. So I don't know, to be honest. So I haven't seen anywhere where the breaking of Lie symmetry or symmetries of differential equations come up. Also, now that you mentioned that, I've seen very little work on finding the symmetries that are discrete for differential equations.
Okay.
So that's now what is now known. So this doesn't answer, this is beyond your question. It just struck me that perhaps I should say this. Well, I mentioned that vector fields that leave invariant discrete equations have also been studied. But these are continuous symmetries, continuous vector fields of discrete equations. So when you study what change of variable leave discrete equations invariant in terms of this business, what you're getting are continuous symmetries. In the same way that I was describing that the circle is, it's all continuous. These are all continuous vector fields. Or continuous symmetries.
Okay, fine.
There was another question at the very back, and then we can see if we have some questions from the online audience. Please.
Hi, sir. Thank you very much for your talk. You shouted out the cosmology group a couple of times, so I thought I'd ask you a question. I wanted to know more about the symmetry breaking examples that, well, we didn't really consider any, and you said it wasn't included in the in the work that you were doing currently. But what would it look like in terms of manifesting it in a formalism like this? I don't know much about it, but I know that it, like in our case, it like works in like early universe and stuff. I'm not asking for a specific application, but how does it manifest maybe in some formalism like this?
Okay, so if it's about symmetry breaking, I got the same answer as I don't know. I don't know where it exists, and I haven't seen it. But just on that, now that you've asked about cosmology and so on. So if you've got these, for example, Minkowski manifold, or you've got the de Sitter manifold and so on, each of them have these metrics that generate your geodesic equations. What we would do is say, actually, it turns out those geodesic equations are Euler-Lagrange equations. They come from a Lagrangian. And in the old days, when we saw Lagrangian, we screamed. Because why? Noether's theorem. So that's where I get excited about the kind of things you're doing. Say when you're taking a metric and you're writing down what you would call a geodesic equation, what we would call Euler-Lagrange equation.
So I think the symmetry breaking would probably be in the solution rather than in the equation. So
yeah, highly likely.
Something.
Yeah,
okay,
sure.
Thank you.
Donovan, do we have some questions from the online audience?
Just the one.
Please.
It's a question saying, is there a way to solve a non-linear system?
In fact, short answer, yes. In fact, the KdV equation is nonlinear. Your Burgers equation, they work nice, they work best, optimal when you're dealing with nonlinear equations. In second order ODEs, the linear equations are problematic. Luckily, we have a very nice linear equation, y double dash equal to 0, which generates a maximum algebra, 8 vector field. And every linear or linearizable second order differential equation can be mapped to that target equation, because that's the way things are. But in general, nonlinear equations, this method really works very nicely.
Okay, then I think it's time to thank our speaker. Thank you very
Thank you.
much. And today, I won't forget that I have to give you a little gift.
Oh, thank you very much.
Sign of appreciation. Yeah. And you see, we're getting more elegant now. We have also a bag to put in the Bizarco magazine. Thank you very much. According to plan, there should be some snacks and drinks outside. Yeah, thank you very much. Please join us there.
Okay, help. Thank you very much for giving me the opportunity.